So for a brief review of 152 kinetics, these are literally my kinetics slides from when I taught 152. So when we're looking at reaction rates, we've got an overall reaction briefly drawn out, okay, right here. So we've got those reactants with their corresponding coefficients as subscripts. The rate law for that general reaction tends to follow the pattern shown below, okay, in the blue box. One of the observations that is kind of important to note is that the orders of those, and the order is what's shown as a superscript, theoretically or not theoretically have to be proven experimentally, okay, proven or determined experimentally. And that's where we'll look at that in a little bit later. Okay, so K is our rate constant, and then those brackets, and this becomes an important observation, that bracket means concentration of whatever is within that. This is going to become an important observation. So in this case, that would be the concentration of A. How do I calculate the concentration of A? It would be the moles of A over the liters of solution. Okay. Why has that become an important thing to note? Well, how could I change the concentration? Okay. You may or may not have been tested on this in 152, but let's say I doubled the concentration. How do I double the concentration? So double concentration of A. How did I do that? Well, one easy answer would be to say, well, I have twice the amount of moles of A. And that's probably where you went if you saw this question in 152. In ochem, we make it a little bit more difficult. How else could I double the concentration of A? I could half the solvent. Okay? If I half the volume of the solvent, what happens? Well, I divide by a half, which means I've done twice the concentration. So we need to be aware that our concentration is dependent on both the substance that we're observing, in this case our reactant, and the solvent. Even though the solvent doesn't explicitly show up in our rate law, it is implied in that concentration statement. Okay, so this is huge. You will see test questions on this, so be aware of that. Okay, so let's clear all that away so we can look back at this. So we've got, again, our rate expression, which shows this. In ochem, we keep it simple. We're just looking at the reactants. The orders have to be proven experimentally, and those orders can range from pretty much any numerical value. So what is order? Okay, well, the numbers that you're seeing there, those orders, are the math. Okay? They're the mathematics that allow us to solve those expressions that you may or may not remember from 152. Chemistry reference for the order is trying to make the math understandable through the language of English. Okay? So what does that mean to us? Well, if we go through and look at kind of the importance of that species in the reaction, that's really what our order is. Okay, so if we looked at the order where that value was a 0, well, what's the importance to that reagent? Well, that reagent isn't involved in the reaction at all. So if we wrote out an example rate law, rate equals K, concentration of A to the 0th order, okay, well, A to the 0th is 1, so our expression becomes rate equals K. Okay, that means the concentration of A had nothing at all to do with the rate of the reaction. Okay, so it becomes a bystander. What happens if instead of it being a 0 order, it was a first order? Okay, well, now what we're saying is that species is involved in the rate limiting step for our experiment. Okay, so it's involved. If that number jumps up to a 2, I would now say it's super involved. Okay, it is involved where it is now having a quadratic effect or a square effect on our overall speed of the reaction. So it becomes really, really important. And then if for whatever reason it jumped up to 3, and we'll discuss why 3 isn't super important for us, now it's all that reagent. To get an order of 3, that means that's it. Okay, A is now the only thing involved in the rate of that reaction. Okay, it doesn't mean it's the only thing involved in the reaction. It just means it's important in the slow step of the reaction. Okay. Okay, why is it now an it's all me thing? Because roughly what these things are saying is that if we look at a picture of what's happening, okay, so if we look at this kind of pictorially, you know what I'm saying, pictorially, in a bystander, we don't see A at all. Okay, so A is effectively a ghost. It's not involved in our rate for our reaction. If it is involved, we could see A present. Okay, if it is super involved, now we're getting effectively 2 A molecules present in our reaction. So some chemistry is happening between 2 molecules versus just between 1. If we move to the third order, we're now saying we need 3 of those molecules involved. Okay, why does it now become it's an all me situation? Well, what we're saying is that is important in the rate limiting step. So this is one step. So if I'm now saying the rate is a third order with respect to A, all 3 of these molecules need to interact with each other at the exact same time. Okay? In a second order, these 2 molecules need to interact with each other at the exact same time. Okay? First order, it's only that single molecule reacting in that slow step. Okay? So why, when we get to the third order, is it become all about that single atom? Well, or that single molecule? What are the odds you're going to get 3 people together to all agree on something? Just look at freaking politics. It doesn't happen. Okay? And you can be like, oh, well, sometimes things work. Then push it to the extreme nasty threesomes. How often do you successfully get threesomes to occur in the real world? Okay? It just doesn't happen with any real frequency or success. Okay? You don't get polygamous relationships easily. Those are challenging things to get to function, which means when we're looking at mechanisms for ochem, getting 3 molecules to all interact with each other just isn't likely. That doesn't make sense. So if I'm going to try and create a mechanism, I don't want to bring in a third molecule unless I really feel I have to. Okay? So when we're looking at our orders for reactions, we're really only 0, 1st, or 2nd. And for that matter, the 0 order means it wasn't involved. So if I'm looking at creating a mechanism, I don't really care about that one either. Okay, so the only 2 orders that I care about are 1st and 2nd order. Okay, if we think back to our discussion of substitution reactions, we said there were 2 types of reactions. Okay, we had them stepwise, and stepwise I know is a new word. Okay, we said break, and then we said make, right? Or we said the second step where it all happens simultaneously, and since that's not a new word, I'm not going to write out its definition. Okay, so it all happened at once. Okay, and we had those numbers kind of floating out there arbitrarily. And you might have heard people saying, well, but stepwise meant it was 2 steps. Okay, why am I referencing it as the 1 type and not the 2 type? Well, it's being referenced as the 1 type because the order of the reaction, when it's stepwise, is 1st order. When it's happening all at once, all of those molecules have to interact with each other at the exact same instant, which means 2nd order. So when we're talking about SN1 and SN2, those 1 and 2s are referencing the rate law for the reaction, the order for that mechanism to occur. It has nothing to do with the number of steps. It has to do with the order of that reaction, okay, or the importance of the reagents in the reaction. Okay, we will see that again later, just kind of giving some background and pushing forward to get a little bit more information on it too. Okay, mathematically, we could go through and reference these as molecularity, and you'll hear unimolecular, bimolecular. Okay, for our SN1, you will sometimes hear it referenced as a unimolecular substitution. Why unimolecular substitution? Because again, that 1 is referencing the order, the unimolecular aspect of it. Okay, and SN2 is bimolecular. SN2, the 2 referencing the bi of our rate law. the one referencing the uni of our rate law. Okay? And that's where those terms are coming from. So, reactions and rate laws, if we went through and looked at these, you may notice that in some of these cases, the orders match the coefficients from the equation, order here being 1 and 1. When I move to the next one, the order 2 for Cl2, 2, but it's not 2 there. Okay? And when we looked at it in Gen Chem, we were looking at overall reactions, and we said we had to then come up with ways to predict mechanisms. So the orders did not match the rate laws, okay? Because those were written as overall reactions. In ochem, things are a little bit different, because when we look at ochem, we will look at rate laws for mechanistic steps, okay? And because we now shift our focus, because we're looking at an entire mechanism, we can say which of those steps do we predict to be the slow step. Once we've identified that, we now know the rate law, the orders match. We don't have to do all these fancy calculations. Okay? That does make the assumption that we are assuming that to be correct, and in theory, there's got to be an experimental setup behind it. That experimental setup we'll see in a second. Okay? So, if we're thinking about rate laws and rate limiting steps, if we think about how long it takes us to get to campus, like right now, it's infinitely long time to get to campus because campus is shut down. We're not allowed to be there. Okay? But if we looked back when we were allowed to be on campus, what slowed us down the most in that time to get from home or for wherever you are to campus? Okay? That is your rate limiting step. Okay? That's your rate determining. So if my rate determining step is how long it takes me to drive to campus, it doesn't matter that I can brush my teeth 5 seconds faster at home. That's not going to have a large effect on the rate of me getting to campus. Okay, does that make sense? But if I drive 70 miles an hour as opposed to 40 miles an hour on the freeway, number one, I'll probably hear a lot less honking. I'll get to campus faster because that was changing my rate determining step. So when we're thinking about our reactions and our mechanisms, our focus is always on that rate determining step. The other steps still happen, okay? They're still necessary for me to get to campus, but they don't affect the overall rate. And because of that, I can ignore them to a first approximation. Okay? So our slow step is always controlling the rate of a reaction. So if I went through and wrote out a rate law, so let's take a look at a quick experiment. Here's a leaving group. Here's a nucleophile. And I want to run this experiment. Okay? I could write out a rate law for this. I could say the rate is equal to the rate constant times the concentration of the species with the leaving group. Okay? And I could say, well, there's my rate law. Okay? Because in that approach, what I'm saying is that the mechanism for this overall reaction is that the leaving group has to leave first, then the nucleophile in a second mechanistic step would come in and attack. In that second mechanistic step, I don't care about it because that's a second step, and I'm saying the most important step is this first one, that this one's the slow one. Because it is the slow one, my rate law is only going to be dependent on the reactants in that slow step. Okay, the nucleophile is present, but it's not doing anything in that first step. So I would say my rate law was rate times K times concentration of the substrate. Okay? What if I decided the second step was my slow step? Okay? This one becomes a lot more challenging if this was a valid mechanism. Okay? Well, in this case, what are my reactants? Well, I don't have that structure anymore. I would have the one with the positive charge, and then I would have the leaving, or not the leaving group, sorry, the nucleophile. Okay? So now the order of my reaction becomes second order because I have two species and their respective orders are first order. Okay, so now my rate law would change. Okay, and as you may or may not remember from 152, we now have a problem with this rate law because this piece is not something I can measure the concentration on. And because it's not easily measured, I'd have to do a whole bunch of other things to try and calculate it. Thankfully, ochem, we don't have to stress on that, so don't worry about it. But this is just trying to elaborate on how these different mechanisms and rates could be explained. Okay, so hopefully that makes sense. Where this would ultimately end up going is that we would have to drive to an experiment. We'd run the experiment, varying concentrations of substrate and nucleophile to decide how it affected the rate. Okay, so just to give you a quick walkthrough on this, which you're welcome to stop if you don't want to look at this because we don't need it. Okay, we note that those two, the concentration did not change, whereas here the concentration doubled. Okay, so no change versus doubled. Okay, what happened to the rate when I doubled the hydroxide? Okay, well, it looks like the rate roughly doubled. Okay, so if I'm now going to write out a rate expression, rate equals K, is hydroxide relevant to the rate of the reaction? Did the rate change when hydroxide was doubled? Yeah, so the concentration of hydroxide is important to the overall reaction. How important is it? Well, it did the exact same thing. It just doubled. Okay, it didn't quadruple the rate. Okay, it didn't go by a square. It didn't go by a cube. It just doubled, which meant the order for the hydroxide was 1. This is way oversimplified for the record. Okay. So we could also go through and try and figure out what about for the other species. So we could try and pick an experiment, okay, say comparing 2 and 3, where here we doubled it. Okay, why expect 2 and 3 as opposed to 1 and 3? Well, if we look at 1 and 3, the hydroxide also doubled, okay, which is going to make the change in the rate more difficult to interpret. So if we compare 2 and 3, the rate also doubled. So again, what does that mean? That means our reaction is also, God, of course I picked a huge freaking thing, CH2Cl, okay, is also important in this reaction because it was a 1-for-1 change. Okay, it was first order, which means according to the mechanistic detail of this experiment, I know that this reaction was a bimolecular reaction, which means in the slow step of the reaction, okay, this species is present and this species is present. Okay, what does that mean as far as my mechanism? That means these two species have to interact with each other at the exact same instant to make our product. How does that work for us as far as the reactions we've talked about? Well, the hydroxide attacks, breaks the chloride at the exact same instant, and we now have a mechanism that explains that rate law. Okay? Like I said, we'll look at it in detail in probably the very next video, and by probably I mean literally the very next video.